Here's an example of using polar coordinates and trigonometric identities to make our lives better. So let's suppose that we are working on computer graphics. Computer graphics are often stored as lists of points, and each point has a different color. So for example, here's just a single point. And I've labeled the coordinates of this point with a subscript because we have to imagine that there are lots and lots of points making up our picture. So each point would have a different subscript. So we'd have x sub 1, y sub 1, x sub 2, y sub 2, and so on. So this n is really a stand-in for some number that tells us which point we're on. Typically, images are made up of thousands or even millions of points. And let's suppose that we want to rotate this picture around the origin. So computers typically store these points using their Cartesian coordinates. And so if we want to rotate this point, this entire picture around the origin of this coordinate system, that would send this single point maybe over to here. So something like this. And our problem will be to figure out what are the Cartesian coordinates of the new rotated point. And we do need the Cartesian coordinates because, again, computers typically store and manipulate graphics using Cartesian coordinates. All right, and let's suppose that the angle that we're rotating this point, let's call this phi. I don't want to call it theta because I'm going to use theta for something else. Okay, so our job is to figure out what are these new coordinates for this point. And we have to keep in mind that really there are thousands or even millions of points that we're going to do this with. So you might notice that if we wrote this point x sub n, y sub n in terms of polar coordinates, then its polar angle theta would show up right here. And then the polar coordinate for the rotated point is just theta plus phi. And so that's a good place to start. Let's imagine describing to the computer how to get the polar angle and then add phi and then get back to the Cartesian coordinates. So first you'd start with x sub n, y sub n. Now we need to somehow tell the computer how to figure out the polar coordinates of this point. So the polar coordinates of this point would be r comma theta, but r is the square root of x squared plus y squared. We'll ignore for the moment the fact that you might need a minus sign here. And the theta coordinate will be inverse tangent of y over x. And we will also ignore the complication that really you might need to add pi to this. Okay, so these are the polar coordinates for the point. And I guess really I should have some subscripts here. So this is x sub n, y sub n, y sub n, x sub n. Okay. And then to rotate this point, x sub n squared plus y sub n squared. To rotate this point, we need to take our theta coordinate, which is inverse tangent of y sub n over x sub n, and then add phi to that. So these are polar coordinates. But so this is the transformed point, the rotated point. But remember, we need the rotated point in Cartesian coordinates so that the computer can actually draw the new point. So just to abbreviate things, this r value here, let's call that r sub n, the r coordinate for the nth point. Okay, and this inverse tangent of y sub n over x sub n, that's theta, really theta sub n. And we're adding phi to that. So our transformed point in polar coordinates is r sub n comma theta sub n plus phi. And then we need to convert this back into Cartesian coordinates so that the computer can actually draw the transformed points. And in Cartesian coordinates, the x-coordinate is r sub n times cosine of the angle for our transformed point, which is theta sub n plus phi. And then the y-coordinate, in Cartesian coordinates, the y-coordinate is r sub n times sine of theta sub n plus phi. And so this is the transformed point in Cartesian coordinates. So let's look at how much work we had to do to figure out this transformed point in Cartesian coordinates. So to get to this point, the original point but in polar coordinates, we needed to do 2 squarings. Let's see how to write this. So we had 2 squarings. We had a sum that's adding the sum of the squares. We had a square root. We had a quotient. That's inside the inverse tangent here. And then we also had an inverse tangent. Okay, then to get to the second line, we had an addition because we had to add phi. Okay, and then to get to this final step, we had to do a cosine, a sine, and 2 multiplications. Okay, so 2 squarings, a square root, a division, a sum, an inverse tangent, another sum, a sine, a cosine, and 2 multiplications. But keep in mind that we have to do each of these operations for every single point that we're rotating. And remember, a typical image consists of thousands or millions of points. So this is an awful lot of work to have to do millions of times. Addition and multiplication isn't too bad. Computers are pretty quick with addition and multiplication. But division is a little bit slow, square roots are quite slow, and trig functions are typically very slow. Okay, so these operations that I've circled, these are the slow ones, and since we have to do these for every single point, this is going to be a lot of work. And by a lot of work, what I mean is it's going to take the computer a long time. So it will take our system a very long time to rotate all these points, and that means, for example, that you couldn't really do this sort of image rotation on the fly or in real time. It would take a computer just too long to do all the calculations. But, you know, there must be a better way, or else I wouldn't be making this video. And if you look at this final result for our point in Cartesian coordinates, it has a sum inside of these trig functions, and that means we could use the sum rule for these trig functions. So let's see what that would give us. So this would be r sub n times, so now we have to write down the sum formula for cosine. This is cosine of theta sub n times cosine of phi minus sine of theta sub n times sine of phi. So that's the x-coordinate of the rotated point. And then for the y-coordinate, it's r sub n times, and now we need to write the sine, the sum formula for sine. And that's sine of theta sub n times cosine of phi plus cosine of theta sub n times sine of phi. Okay, this is all in Cartesian coordinates. And it seems like we haven't really helped ourselves because we still have all of these r sub n's and theta sub n's. And remember, finding r and theta takes a lot of work. And also we have lots and lots of sines and cosines all over the place. And sines and cosines also are a lot of work. But before we give up on this idea, let's take this r sub n and we'll distribute it like this. And we'll do the same thing in the y-coordinate. We'll distribute r sub n. And we end up with r sub n times cosine of theta sub n times cosine of phi minus r sub n times sine of theta sub n times sine of phi. So that's all for the y coordinate. I'm sorry, all for the x coordinate. Now for the y coordinate. R sub n times sine of theta sub n times cosine of phi plus r sub n times cosine of theta sub n times sine of phi. And this is in Cartesian coordinates. So it still looks like we haven't really made any progress because there are r's and thetas all over the place and sines and cosines all over the place. But if you look carefully, right here, r sub n times cosine theta sub n, that is x sub n times cosine theta, I'm sorry, cosine phi. And then the next part here, r sub n sine theta sub n, that's minus y sub n times sine of phi. So that's all for the x coordinate of the rotated point. Then for the y coordinate of the rotated point, r sub n times sine theta sub n, that's y sub n times cosine phi plus, and then right here, r sub n times cosine theta sub n, that's x sub n times sine phi. Now this seems like an improvement because there aren't any r's, so let's count up all the operations that we have to do for each point. Well, to get x sub n, remember we started out knowing x sub n, so we don't have any calculations to do to find x sub n. We already know what x sub n is. Same for y sub n. We start out knowing that. We know y sub n, we know x sub n. So our only operations are this cosine phi and sine phi. We have to calculate cosine phi and sine phi, so that's a cosine and a sine. But for all of our millions of points, sine phi and cosine phi are going to be the same because all of the points are being rotated by the same angle because they're all part of the same picture. So these cosine and sine phi, we don't have to do this millions of times, we only have to calculate those one time. And then the remaining operations, there's a multiplication here, 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 and here, so 4 multiplications. So 4 multiplications. But we're going to have to do this multiplication for each of our millions of points. So 4 times multiplication, this is per point. And then also we have this subtraction and this addition. So an addition and a subtraction. Also, we have to do those per point. Okay, so comparing this to our original idea for finding the Cartesian coordinates of the rotated point, if we just scroll up, for every point, at first, for every point we had 2 sums, 2 squarings, a square root, a division, an inverse tangent, a sine and a cosine, and 2 more multiplications way down here. And we had to do this for every single point. So all of these operations we had to do millions and millions of times, once for every point. Using this new method, for each point we have to do 4 multiplications, an addition and a subtraction, and then only once at the beginning, 1 cosine and 1 sine. So all of these operations, this is much, much less work than we had to do using our original idea. And also all of the operations that we have to do for every point, remember multiplication, addition, and subtraction, these are all of the cheap operations. These are the fast ones. So the operations we have to do per point are all very fast. The only complicated operations, the sine and the cosine, we only have to do those once at the very beginning. We don't have to calculate those for every single point, only once at the beginning. So this new way of calculating the rotated points, this is something that computers can do very quickly, and so they can do it in real time. So using this method, computers can do it fast enough to, say, make animations, or to say be part of the graphic system in a video game where the computer is calculating new pictures 60 times per second, so it looks realistic. So this is just one example of how trig identities and polar coordinates gets used in computer graphics to make things practical.